Programs often need to make decisions to do one thing if a condition is true and something else if it's false. So in Python, decision making is done using control structures like if, elif, and else. Let's start with the basic structure of an if statement. So you write if and then condition. So you can see the if condition block. So you write if keyword and then condition comes, then colon, and then one tab indented statements. Remember, Python uses indentation instead of curly braces to define blocks of code. Usually we indent by 4 spaces. When you enter a value, Python checks the condition age is greater than is equals to 18. If it is true, it prints you are adult, otherwise the else block runs. We can also chain multiple conditions using elif, short for else if. For example, Python checks each condition from top to bottom and executes the first one that is true, then skips the rest. This makes control structures powerful and easy to read, one of the reasons Python is famous for its clarity. In this example, if you enter 82, the first condition marks is greater than equals to 90 is false. So Python moves on to the next condition, that is marks greater than is equals to 75. That is true, so it prints grade B and skips all the remaining checks. Operators in Python lets you manipulate data from simple math to logical decisions and bit level manipulation. So let's take a quick tour to now let's take an overview of Python's main operators grouped by their purpose. On the left, we begin with the arithmetic operators. These handle basic mathematical operations. The plus sign performs addition, the minus sign is for subtraction, asterisk is for multiplication, and forward slash for division, which always produces a floating point result. Percent sign gives the modulus or remainder of a division. The double asterisk represent exponentiation, such as x double asterisk y means x raised to the power of y. Finally, double slash performs floor division, which rounds the quotient down to the nearest whole number. Moving to the top right, we have a comparison operators. These compare values and return either true or false. Double equals to checks for equality and not equals to checks for inequality. We use greater and less than signs for checking equivalently less than or greater than conditions, and then less than equals or greater than equals when we want to include the equality in the comparison. So these are very common in conditions and loops. Now let's look at the logical operators table. The word and returns true if both the conditions are true, and the keyword or returns true if even one condition is true, and not simply reverses a condition. If something is true, not makes it false, and if something is false, then not makes it true. Finally, we have an identity operator, that is and is not. These check whether two names actually refer to the same object in the memory, not just equal values. For example, x is y returns true if both variables point to the same object. X is not y returns true when they refer to different objects. So in summary, Python operators help us perform calculations, comparison, and logical tests efficiently, and understanding which operator to use and when is a key to write clear and bug-free code. Python arithmetic is very intuitive, always performs true division and returns a float. In Python, there are 3 closely related division operations. The single slash performs true division, so it always returns a floating point result. Double slash is called floor division. It divides two numbers but then rounds down to the nearest integer, not simply truncating the decimal part. This difference is especially noticeable when we use or deal with negative numbers. For example, minus 3 double slash 2 gives us minus 2, not minus 1. Because Python's floor division always rounds down towards negative infinity. The modulus operator gives the remainder of the division. In Python, it is defined so that this formula always holds. So for minus 3 modulus operator 2, the result is 1. Since minus 3 equals to minus 2 into 2 plus 1. So this consistent rule is what makes division and remainder behave logically across both positive and negative numbers. Python sequence operators make working with strings and lists very intuitive. The plus signs joins sequences together. This is called concatenation. When we write hello plus world, Python builds a brand new string containing both. The originals stay the same because strings are immutable. So we will see what is immutable and mutable data structures in a moment, or objects in a moment. List also support plus, like if we plus two lists, one containing 1, 2 and second one as 3, 4, this gives us a new list 1, 2, 3, 4. This is handy for merging data, but keep in mind it doesn't modify either list. It creates a new one. The asterisk is a repetition operator. Here the string HA into 3 gives this string. For list, subscript of 0 into 4 creates 4 zeros. However, repetition can be tricky with mutable elements. For example, if you repeat a list that contains another list, then the Python reuses the same reference. Appending to one sublist will change all of them. This is because the repetition duplicates the references, not the deep copies of the content. So the rule of thumb is plus and asterisk with sequences always return a new object, but the contents inside may still be shared if they are immutable. Understanding that distinction is essential when manipulating lists in Python. One of the most important concepts in Python is mutability, whether an object's value can be changed after it's created or not. In Python, we categorize objects into two groups, immutable and mutable. Immutable objects cannot be changed after creation. Typical examples are numbers like integer, float, strings, and tuple. When you change an immutable object, you actually create a brand new object and bind the name to that new object. So mutable objects can be changed in place, like list, dictionaries, sets are common mutable types. Mutating these objects modifies the object itself. Any name that refers to the same object will see the change. So let's walk through the concrete examples so the difference is crystal clear. We will also cover important consequences like identity versus equality, function arguments, plus equals to behavior, shallow versus deep copies, and a few classical mutable default arguments. So here are some simple examples considering integers and lists. Code block 1 deals with immutable type like int. X and y initially point to the same integer 10 object with 10 value. X plus equals to 1 creates a new integer object with 11 value and rebinds y to it. Notice that x still references to the original integer with 10 value. For immutable integers, when you do x is equals to 10, y is equals to x, both names reference the same integer object. But if you do y plus equals to 1, Python creates a new integer and rebinds y to it. X still points to 10. You can confirm this by checking with the help of function that is named as id. So id x and id y. Id basically returns the object's memory addresses. For example, mutable list, if a is equals to 1 to 3, b is equals to a, both name reference the same list object. If you call b dot append 4 and list object itself is modified, so a and b both show 1, 2, 3, 4. Their id values remain identical because it's the same object. This difference matters when you pass objects into function. If you pass a list and a function mutates it, the caller sees the mutation. If you pass an integer and the function changes it, the caller doesn't see any change. The function simply rebinds its local name to a new integer object. Here we can see the Python built-in data types, which of them are immutable and which are mutable. Starting at the top, numeric types like integers, float, booleans and complex numbers are all immutable. Once created, their value cannot be changed. When you perform an operation like x is equals to x plus 1, Python actually creates a new object with the updated value and rebinds the variable name to it. Next, tuples, strings and frozen sets are also immutable. Tuples can hold different objects, but you cannot modify their structure. You cannot append, you cannot remove or reassign elements inside them. Strings are immutable sequences of characters. Any operation that looks like it modifies a string, such as concatenation, slicing that we will be covering later on, or replacing a character, always returns a new string object. Frozen set is simply a immutable version of a set. Once created, its contents cannot be changed. On the mutable side, we have lists, sets, and dictionaries. These can be changed in place, meaning you can add, remove, or update their elements without creating a new object. The same list object now contains 4 elements. The variable a still refers to the same memory location. You can verify this again using an id function on a before and after the append operation. Similarly, sets allow adding or removing numbers dynamically, and dictionaries let you update key value pairs on the fly. It is important to remember that immutability brings safety and predictability, while mutability brings flexibility, but it also potentially has some side effects, like if multiple names refer to the same object. So when designing your own class or choosing data structures, think carefully about whether your data should change in place or remains constant once created. Notice how the string x changed its identity. A new object was created, while the list kept the same identity, meaning it was updated in place. Python provides several numeric types for different needs. Int are integers with arbitrary precision. You can have very large integers without overflow. Float follows IEEE double precision, that is fast but can display surprising rounding. For complex maths, Python has a built-in complex type. So a complex number 2 plus 3j has a real and imaginary attributes with dot real and dot imag. When exact base 10 arithmetic is required, for example in financial calculations, use decimal. So decimal avoids such binary float rounding. For exact rational arithmetic, use fractions. Fraction to represent p by q, for example, precisely. So here's a step-by-step example for decimal line. So decimal 0.1 constructs a decimal from a string to avoid float parsing error. Adding two decimals yield decimal 0.3. So this avoids the float, that is 0.1 plus 0.2 float is nearly equals to 0.30000 goes to 4. So left column concise. So Python is dynamically typed, which means you do not have to declare variables ahead of time, but sometimes you will want to manually convert between the types. You can do this by calling built-in type functions like int, float, str. For example, calling int function and passing 3.1415 maybe converts the float into an integer. But notice it doesn't round, it truncates the decimal part, leaving you with a 3. Next, str, let's suppose 3.0 takes floating point value and converts it into a string representation. Float converts a string that looks like a number into a real floating point value. So these conversions are often used when handling user input from the keyboard. Since input function always returns the text, you will usually wrap it into int or float functions if you want to do numeric operations. Strings in Python are sequence of Unicode characters and are immutable. You can index and slice them just like lists, but any operation that changes a string creates a new string object. String methods are plentiful. Dot split tokenizes, dot join concatenates and iterable efficiently, dot replace substitutes, and dot strip removes surrounding white space. When concatenating many strings, prefer dot join and you pass a list of parts for performance rather than repeated plus operations. Strings in Python are ordered sequence of characters, and each characters in that sequence can be accessed using an index. Here we start with the string s is equals to spam. When we call length function of s, Python tells us the length of the string, in this case 4 characters. Now Python uses zero based indexing, meaning that the first character is at position 0, not 1. So s of 0 returns s, the very first letter, and s of 1 gives us p, the second letter. In addition to counting from the left, Python also allows negative indexing, which is an incredible useful feature. Negative indices count from the end of the string, like s of -1 refers to the last character, which is m, and s of -2 refers to the second to the last character, that is a. So positive indexes count forward starting from 0, and negative indexes count backward starting from -1. So this makes it very easy to access any part of the string without needing to know its total length. For instance, s of -1 will always get the last character no matter how long the string is. After indexing individual characters, let's move on to slicing, and this is one of the most powerful features in Python sequences. Slicing allows us to extract a subsequence from a string. Here's how it works with our string s is equals to spam. When we type s1 colon, then Python starts at index 1, the letter p, and takes everything up to the end. The result is spam. Notice that the original string is still spam because strings are immutable, so slicing always produces a new string, leaving the original one unchanged. Next, s of 0 colon 3 means start at index 0 and stop right before index 3. This gives SPA everything but the last character. You can shorten that even further. For example, s of colon 3 works the same way because Python automatically assumes the start index is 0. Similarly, negative slicing works too. Like for example, s of colon -1 means take everything up to but not including the last character. Again you get SPA. Finally, s of colon gives a full slice, that is a copy of the entire string from start to end. This is often used when to make a top level duplicate of a string or a sequence. So remember, in slicing, the start index is inclusive and the end index is exclusive, meaning Python stops just before that position. This rule is consistent across all the Python sequences types, not just strings. We already know strings are sequence of characters, but another important property of the strings is that they are immutable. That means once a string is created, its contents cannot be changed in place. Let's explore this using one familiar example. We start with s is equals to spam. If we write s plus xyz, the Python performs concatenation. It joins the two strings together, returning a new string spam xyz. But notice, the original s is still spam. The operation didn't modify it, it just created a brand new string object and returned it. If we check by trying to assign directly s of 0 is equals to z, for example, the Python raises a type error and the message clearly says that the string object doesn't support item assignment. That's Python way of reminding us that string objects are immutable. However, you can build a new string from the parts of the old one, for example, by taking everything except the first letter and prefixing it with a maybe letter z. So this statement does the same. Now the new value of s is zpam. Essentially, you are not modifying the old string, you are creating a new one and assigning to the same variable name. Behind the scenes, Python automatically handles memory management and cleans up the old unused string when it's no longer referenced. So the key takeaway here is that strings are immutable, but names are not. You can rebind a name to a new object whenever you need to. Let's look at two more common operations you can perform with the strings, that is repetition and membership testing. First, look at repetition operator, that is represented with a steric sign. When you multiply a string by an integer, Python repeats that string that many times. For example, if you write s steric 3, this gives you this string with spam word repeated 3 times. So this doesn't modify again the original one, remember, as the strings are immutable. So instead, Python creates a new string that is a concatenation of 3 copies of spam. So this operator is really handy for the task like generating repeated patterns, in maybe formatting and creating separators in text output. Next, the membership operator. It checks whether a substring exists inside another string. A in S returns true if A is indeed one of the characters in or string that is spam. But Z in S returns false because there is no Z in our string. So you can also reverse the test using not in. For example, am not in S returns false because am is found inside spam string. Membership testing works not just with strings but with any sequence in Python like list, tuple, or even dictionaries, where it checks for the presence of elements or keys. So X is for repetition, that creates multiple copies. In and not in are for searching within the sequences. Python strings come with a powerful set of built-in methods that lets us manipulate and search text very easily without needing any external libraries. Let's start with two commonly used methods that are find and replace. Find method is used to search for a substring within another string. The method returns the offset index where the substring first appears. For example, s is equals to spam, calling s.find pa returns 1. That's because the substring pa begins at index position 1. So remember, Python uses zero-based indexing. If the substring is not found, .find returns -1, which is handy for conditional checks. Next we have replace function, which creates a new string by replacing one substring with another. When we write s.replace, Python scans the string, finds the string pa, and builds a new string that is sxyzm. Notice again that the original string hasn't changed, it is still spam. So this behavior enforces that strings are again immutable. Both the find and replace return new values without modifying the original object. So these methods are commonly used in real world tasks like searching within the documents or maybe cleaning or formatting data. So here find returns the first index of a string na, that is 2. When we try to find x, it returns -1 because the substring doesn't exist. Replace method replaces all non-overlapping occurrences of na with capital Na, giving this string, but again the original text remains as it is. Python strings are not just static piece of text, they come packed with powerful built-in methods that make text processing incredibly simple. So let's start with one of the most useful method, that is .split, the split method. Here we have line is equals to that string. When we call line.split and we pass comma in the split function as an argument, the Python looks for each comma and splits the string wherever it finds one. So you can see the result as a list of substrings. So this is extremely common when reading comma separated values during parsing data files or handling user input that comes in, for example, in a single line. Next is an upper function. Upper converts every character to uppercase, giving you all the string characters in uppercase. Similarly, lower would convert everything to lowercase. Now what if you want to test what kind of content your string holds? So Python provides a family of boolean test methods like isAlpha, isDigit, isLnum. When we call isAlpha, it checks whether every character in the string is a letter and returns true. If s contained digits or punctuation, for example, it would return false. These methods are extremely handy in input validation, for example, checking that the user has entered only the letters in the name field or only digits in the phone number, for example. Here isDigit confirms that all the characters are of digits. isAlpha returns false because it includes numbers, but text.isLnum returns true since it contains only letters and digits. And when you use .split with no arguments, Python splits on white space by default, that is for spaces, tabs, and new lines. Lists are go-to mutable sequence in Python. Use append function to add one item, extend to concatenate from an iterable, insert to put an item at a position, and then pop to remove and return an element. List comprehensions are efficient. For example, you can write this thing in a square bracket. So slicing L start stop creates a new list. It doesn't mutate the original. Note that repeating list with static duplicates the references. If elements inside are mutable, they will be shared across repeated slots. So this expression inside the square bracket, as you are seeing on the screen, iterates elements from 0 to 5 and computes the squares, returning a new list with 6 values. So comprehensions can include conditions like this for evens. For copying, use list.copy for shallow copy and copy.deepCopy function if you need to clone nested mutables. So far we have worked with simple list that contains numbers or strings, but in Python list can actually contain other lists. In Python lists can contain other lists, and that's what we call nested list. Let's look at an example, L_nested. You can think of it as a list of lists. Each small list inside is like a row of data. So in this structure, L_nested is our outer list because it holds other lists, and each 1, 2, 3, 4 and 5, 3 is an inner list. So if we access L_nested 0, we get a first inner list, that is 1, 2. But if we go one level deeper, that is L_nested, we supply two subscripts 0 and 1. That means we access the second element inside the inner list, which is 2. This kind of structure is very common when dealing with tabular data, matrices, and multi-dimensional arrays. Visually, you can imagine a big container, that is outer list, holding several small containers, the inner list, each small one containing its own values. So understanding this structure is very essential before learning about the concepts of shallow and deep copies, because when you copy a nested list, you have to decide whether to duplicate just the outer container or all the inner ones as well. Now let's explore what happens when you try to copy or repeat lists in Python. At first glance it looks simple, but there is an important concept underneath that is called shallow versus deep copying, and it can lead to maybe confusing bugs if we do not understand it carefully. Let's start with a repetition example. Here we start with a is equals to 1, 2, 3. So this is stored at memory address 5000. When we create b is equals to a into static 3, the Python doesn't make 3 new lists. Instead, it creates one outer list at address 6000 containing 3 references pointing to the same inner list object at address 5000. So if we change a value inside one of those inner lists, say b0 of 0 is 99, all 3 will appear updated because they all point to the same memory object. Python's list repetition doesn't create new list, it repeats the references to the same underlying object. So in memory, all 3 elements of b are actually pointing to the same list object, a. When we print b, we see it looks like 3 separate lists, but they are actually all connected. Watch what happens if we modify just one sublist. For example, b0 of 0 is equals to 99. Now all 3 sublists show 99, 2, 3. That's because they are all referring to the same inner list in memory. This is why we say list repetition repeats references, not copies. Now let's move on to shallow versus deep copying concept, which gives us a better control. Python provides 2 main ways to copy object: shallow copy and deep copy. Shallow copy, which makes a new outer list but still references the same inner objects. Deep copy, which makes a completely independent clone, that is both the outer and inner elements are duplicated. Let's see this in action. Suppose we have a list L1 containing 2 inner lists 1, 2 and 3, 4. we make a shallow copy using L1.copy and deep copy using copy.deepcopy. Now if we modify L1 of 0 is 99, then change affects both L1 and L2 because they share the same inner list. Shallow copy makes a new outer list but doesn't make new copies of the inner list. So here L1 and L2 have different outer list addresses, maybe 7000 and 7100, but both still references the same inner list, that is 7200 and 7300. So if you modify one of the inner lists through L1, that change also shows up in L2 because both share the same inner objects. So in contrast to this, deep copy duplicates everything. Python builds an entirely new outer list and recursively copies inner list too. So now L1 and L3 point to completely separate memory addresses, both inner and outer. That means modifying L0 will not affect L3 at all because their inner objects are independent copies. But L3, which was created using deep copy, remains completely unchanged. So shallow copy duplicates only one level of the object structure and deep copy recursively duplicates everything inside. So deep copies take more memory and time, but they guarantee total independence between the original and the copy.